So we are looking at something called a molar concentration of a solution. Now, are you guys familiar with the concept of concentration?
Yes.
Yes? Like ish?
Ish.
Ish. So if I was to say, here I have 1 liter, okay, and I have there are 6 dots in there, and we're going to say that represents 6 moles. Okay, and we have another beaker over here. And we have 3 dots, which represents 3 moles. Which of these two is more concentrated and which one is more dilute? Chat with your partner. If you don't have a partner,
That one's concentrated kind of, and the other one is dilute. Yes.
the one on the left is more concentrated. And the one on the right is more dilute. Now, the reason I'm saying that the dot represents a mole is that when we dissolve things, we're dissolving like hexillions and hexillions of particles, yes? So just counting individual particles doesn't make any sense. So we count them by moles. We say there's 6 moles of this substance in 1 liter. Okay, so how we would express this is for this one, we would say there's 6 moles of dots. Obviously, we would normally have a real chemical formula there, but 6 moles of that per 1 liter. And that is the concentration. Six moles per 1 liter, 6 moles in 1 liter. Now, if we have this one over here, I'm just going to put conc for concentration, and that is equal to 3 moles of dots per 1 liter. Does that make sense? So we have the one that is more concentrated has a higher concentration, more moles per liter. And the one that is more dilute has a lower concentration, fewer moles per liter, okay? So we have more moles per liter. And this one we have fewer moles per liter. Do you guys know where everyone is today? Like, why is half my class gone?
Oh,
Okay.
God. There's like the market thing. Volunteering.
Oh, okay. Okay, so there's many, many things. Alrighty. All right. So that's what we're talking about here. And then let's just review a little bit of what a solution is. Okay, so a solution is a homogeneous mixture. Do you remember that part? Homogeneous mixture. What does it mean to be homogeneous?
Look the same.
It's all the same throughout. Okay, there's no one area that is different from another area. All right, and if 2 substances are mixed, the substance that is present in the smaller amount is called the solute, and the substance that is present in the larger amount is called the solvent. Okay, so we have the larger amount is the solvent, The smaller amount is the solute. And the solution is a homogeneous mixture. So, there are tons of different kinds of solutions. In fact, air itself is a solution because it is a mixture of, it's a homogeneous mixture of oxygen gas and carbon dioxide gas and mostly actually nitrogen gas. But we don't deal with those kinds of mixtures very much in chemistry 11. Mostly what we do is we have a liquid solution. So very often what we're doing is we are dissolving either a solid or liquid or gas solute is dissolved in a liquid solvent. So that's the kind that we mostly use in chemistry. Can you guess what the liquid solvent is usually? It's usually water. Okay, and so we call it an aqueous solution. And we can now say that the dissolved solute is represented by aqueous, and for that we use the subscript AQ. So if we're saying the salt in salt water, we would write NaCl, and at the bottom we would write AQ. Dissolved in water. Now, just like we were saying at the top of the page, the concentration is the quantity of solute dissolved in a solvent to produce a given volume of solution. So it's the amount of solute in the solution. So concentration equals the amount of solute per volume of solution. I should have left more room for that, shouldn't I? So conc, or conc with a little n at the top, is one of my abbreviations for concentration, okay? So basically we need an amount in the numerator, okay? And we need a volume unit in the denominator. So what are some ways we could measure the amount? Well, we could measure amount in grams. We could measure the amount in milligrams, or we could, and this is what we are mostly going to do this year, we could measure the amount in moles, okay? On the bottom, we have the volume. We have the volume. It could be liters, it could be milliliters, okay? But as long as you have amount over volume, that is concentration. Now here's a little tricky thing to think about. Concentration is expressed as the quantity of solute, so we have the solute on the top, over the volume of the solution. Okay? It is not the quantity of solute over the volume of the solvent. That is not correct. So we're going to take a look at a little picture here. On Monday, when we have a little more time during class, we'll actually make a solution. Okay? So basically, if you want to make, say, 1 liter of solution, and this is a 1 liter, does anyone remember what this flask is called? No, it starts with a V. Volumetric, and it's got 1 line on it right here, and that line represents when you get to exactly 1 liter, okay? So if you want to make 1 liter of solution, you're not going to use 1 liter of water. And the reason is, let's say we want to make a 1 mole of NaCl per liter solution. What we will do is we're going to add 1 mole of NaCl. And we'll do that. How can we measure out 1 mole of NaCl? Where would we have to look to figure that out?
At the periodic table?
At the periodic table, because that will give us the molar mass. And remember, molar mass is what?
Atomic mass.
Molar mass is the same as atomic mass. Except it is the mass of how much? How many particles? Yeah, molar mass is the mass of 6.02 times 10 to the 23 particles. In other words, i.e., it is the mass of how much? 1 mole. Okay, so the molar mass is the mass of 1 mole. That's why it's molar, because it's per mole. So if we go on to our periodic table, Na is 23.0 grams per mole. Cl is 35. I'm going to use their point. I'm going to just say 35.5 grams per mole. This is using our periodic table. And you would get the 2 of those together. If we add them, we get 58.5 grams per 1 mole. Now, whoever was doing this was using a different periodic table than ours. Our periodic table only goes to 1 decimal place. Their periodic table goes to how many decimal places? 2 decimal places. That's fine, doesn't matter. So their molar mass is a little bit more precise, okay? So what I would do is, if I were the person doing this, I would say, I want to have 1 mole of NaCl in this 1 liter flask. So I'm going to measure out 58.44 grams, and I'm going to use a funnel to dump it into the flask. Okay, so we have a funnel here. And what did we call this kind of flask again?
Volumetric.
That is a volumetric flask, so you can label that volumetric flask. Okay. And what you would do is you would add some water until it gets about halfway full. Okay, so I'm just going to fill this thing up halfway full. I don't have any solute in here right now, so it's kind of boring. We'll do the actual thing on Monday when we have more people here and more time. Now, if I had solid in here, it would be sitting down at the bottom, yes? How would I get it to dissolve? I would swirl it. Now, why would I not fill it right up to the line just to start with? Because I can't swirl it, right? So halfway full, so we can swirl. There will be a quiz on molarity and concentrations, and this procedure will be on there. It won't be on, we won't have a quiz on that until after we've done it ourselves at least once, if not twice. Yes? But this whole procedure, you can imagine, okay, we take the funnel, we put our solute in the solid, and then we fill it up halfway. Why don't I just fill it up right away? Because I need to swirl it. Okay, so I swirl it until it's all dissolved, and then I can add water up to the 1 liter line. Okay, and I normally would not do it like this. Well, I could do it like this for a really big volume like this, but you can see my line is right there and I went over. Is that a good thing or a bad thing? That's a bad thing because I would have to start all the way from scratch again if I go over the line, because I cannot, like, it's all mixed now, right? But what I would normally do is I would normally get close, and then I would start using a water bottle, because that way I can control the flow a lot more. And if I really want to, I can even get a medicine dropper and start going drip, drip, drip as I get it right up to the line. Okay? So now we would have solute in here plus the solvent, and they are now a homogeneous mixture. Okay, and that gives us 1 liter in total. So the 1 liter is the solute plus the solvent, because the solute takes up some space and the solvent takes up some space. So it is 1 liter of solution. Yes,
Can I use the water?
of course. Now, what I want you to imagine is that we're going to do this a second time, but now I'm going to add 1 liter of solvent. Can you see here how the solute already takes up some space? Yes? What's going to happen if I add 1 liter of solvent?
It's going to be over 1 liter.
It's going to be over 1 liter, okay? Solute plus 1 liter of solvent. The volume is greater than 1 liter, and you don't want that. Okay, there's no way of predicting how much more than 1 liter it is, so it's not a good way. So we always just make it per liter of solution. Okay. Okay. Now, as I was saying earlier, we normally, our quantity is usually going to be expressed in moles rather than mass, and our volume is normally going to be expressed in liters. Okay, so we're going to have the moles of solute over the liters of solution, and this is called the molarity. So that's a new vocabulary word, okay? Molarity. Or we can call it the molar concentration to distinguish it from the grams per liter, okay? So 2 new vocab words. So if I say, what's the molarity? You say, what's the moles per liter? The moles divided by the liters. Okay, and we can represent that unit 3 different ways. We can write out the entire unit, moles over liters. We can write it out abbreviated, moles over liters, or we can use the shorthand version, which is written as capital M. And the capital M hides, it's a combo unit. Of moles and liters. Don't write this part down. I don't know if you remember it, but the Newton. Okay, that is also a combo unit, yes? You could actually write a Newton as a kilogram meter squared per second squared. Okay, so we're hiding the kilograms and meters and seconds inside the Newton just to make it convenient, because you don't want to write kilogram meter squared per second squared every time. It's exhausting, yes? If you have force, you just want to say newtons. So similarly, sometimes we write moles per liter, but other times we will write capital M. And we don't say moles per liter when we say capital M. Capital M is pronounced molar. And it means, and you guys should be able to tell me what it means now because it's right beside it. Moles per liter. Okay, so capital M is equal to moles per liter. We spend a lot of time with vocab here because there's a lot of molar concentration. And then, we also call it the molarity. That's how we describe it. Molarity means molar concentration. It means concentration in moles per liter. Okay, so if I say find the molarity, I mean find the moles per liter. But when you use it as a unit, the capital M, you say it is 3.0 molar. Okay, and don't worry, we're going to go through this. Every time we use molar, we'll use all the words and all the symbols and everything. There are 2 ways, 2 methods to write molar concentration of a particular substance. So if I wanted to say the concentration of sodium chloride, the molar concentration of NaCl, I could write it one of two ways. I could write it as the letter C for concentration. And that's a lowercase c for concentration. Or I can write square brackets around the formula. Now, which one am I going to use more? I'm going to use this one. Are you allowed to use the other one though? Totally. Yes? Now, one of the reasons that I use this one is it is so much easier to word process. Okay, because you have a lowercase c for concentration, and then you have a subscript NaCl. Yes? Which is okay. I can do that. You know, do you guys know how to subscript and superscript in Word? Control plus will get you to subscript. Control plus will get you out of subscript. Control shift plus will get you into superscript. Control shift plus will get you out of superscript. If you ever want me to post that on our team, I can do that for you because it's kind of a useful thing. All right. If I ever want to, like, let's say I wanted to do the concentration of Na2SO4, I have to subscript the Na2SO4, and then I have to make the font of the 2 and the 4 smaller, and then make it go down below the line even more. So it's a huge pain in the butt. So I have a tendency not to do that. I would really much rather go concentration of Na2SO4. It's so much easier to type. Okay? So how do we do these calculations? Well, calculations involving molar concentration, which is also known as molarity. So we can write it as C is equal to N over V. Do you remember what N stands for? N. It's not the mass. M is mass. N is the amount of matter. And what's the unit? This is way back from unit 1. Unit is moles. So N represents the number of moles. Okay, so N is the number of moles. So you would, if you're finding the concentration, you put the number of moles on the top, and you put the volume of solution, and it has to be in liters, on the bottom. And then concentration is equal to moles per liter. And how do we pronounce that capital M? Molar. Okay, another way to write it, so you could write your formula this way, C equals N over V. That's one way. And a lot of people like that, so if you like doing that, that's fine. I really prefer this method, and you'll see this much more commonly, especially if you're taking Chem 12, that's how we write it, where you put the concentration of X, concentration of substance X, you would put a substance in there, NaCl or whatever you want, equals moles of X over liters. Okay? Now, volume has to be in liters. If you are given milliliters, you must convert to liters. Do you know how to convert to liters from milliliters? Say we had 500.0 milliliters. At this point, you are allowed to just convert by moving the decimal point. Do you know how many places to move it? A milliliter is 1/1000th of a liter. Those are 3 zeros there, yes? So how many places am I going to move my decimal place?
3.
3 places. And should I have more liters than milliliters or more milliliters than liters to be equal? More milliliters than liters. So I'm going to move my decimal place over 1, 2, 3 places, and that becomes 0.5000 liters. Okay, if I have 25.0 milliliters, I would need to move my decimal place 1, 2, 3 places, which gives me 0.0250 liters. Is good? Okay. Okay, now this question, the answer is given on the other side of the page, but we're going to just do it together here. So don't turn the page, just leave it. You can either just watch me, or if you want to write on a separate piece of paper, you can write on a separate piece of paper. Okay, but don't look ahead. So we have a question, and it says we have 0.025 moles of Li2CO3. Okay, and they are dissolved in enough water to make 460 milliliters of solution. How would we read this last part here? What would we say we are finding? Tell your partner. Find the what? Concentration. Of Li2CO3. And that would be in moles per liter. If we have the square brackets, it always means in moles per liter, not in grams per liter. So we would say, okay, I would like to find the concentration of Li2CO3. Is this a unit conversion or is this a formula? Can I convert moles into moles per liter? Is it possible to have a unit where I do a unit conversion where I start with moles and I end up with moles per liter?
No.
No, I cannot convert. What do I want to do if I'm starting with moles and I want to end up with moles over liters? It's easier than you think. I just take the moles and I divide by the liters. So I take my 0.25 moles and we divide by, and it has to be liters, so we have 460.00. What would that be in liters? 460.0. How many places do we move our decimal place? Move the decimal 3 places. And if you can't remember that, mega, kilo, deci, centi, milli, micro, nano, 631, 236, 9 is for the nano. So milli is 10 to the negative 3. So we move how many decimal places?
3.
3. And hopefully you can remember to move it to the left so that we have a smaller number of liters. So we would have divide by 0.4600 liters. And we would get close. 0.25 divided by 0.46 equals 0.5435. Is that a good answer? No. What's wrong with it? Sig figs. How many sig figs should we have?
3.
2. 2 sig figs. Right? The 0 in front of the decimal. The zeros on the left never count. So we would have 0.54.
M.
Yes, we can either write it as 0.54 M. Tell your partner how you pronounce M. Molar. So we have 0.54 molar Li2CO3. Or you could write it as 0.54. What's the other way we could write it? Moles per liter of Li2CO3. And later on, we're going to be using concentration as a conversion factor. Which version, the yellow version or the blue version, do you think we would use if we wanted to use molarity as a conversion factor? Do we like the yellow version as a conversion factor or the blue version as a conversion factor? Blue version will allow us to convert between moles and liters. We're not there yet. We're not doing that today, but I just wanted to let you know that there is a good reason sometimes to write it as moles per liter. Okay. And let's try this next one here. Okay. So we have 203.082 grams of potassium hydroxide, KOH, is dissolved in enough water to produce 2.00 liters of solution. Find the concentration of KOH. First of all, what is the formula for finding concentration of KOH? What do we put on the top and what do we put on the bottom?
Well,
And you can just give me the units if you like. What goes on the top? Moles. So I want the moles of KOH. And on the bottom, I want the
Volume.
volume. Volume of solution. Question, do I know the moles of KOH? Could you find the moles of KOH? You have grams of KOH. How do you go from grams to moles? What conversion factor do you use? You need something with grams on the top and moles on the bottom, or upside down, right? We need moles and grams. What is a quantity that has a unit of grams per mole? Molar mass. And where do we find the molar mass?
Periodic table.
On the periodic table. So you're going to have to start this problem by finding the molar mass of KOH. Do you guys think you can do that? Give it a try. Did I get the molar mass?
Oh, 39.1, not 39.
After we have found the molar mass of KOH, what would we do next? We eventually want to have the moles of KOH so we can put it in this formula. What do we currently know about KOH? We currently know the grams. We have the grams. We want to convert the grams into moles. Can you do that? Give it a go. What unit would need to go on the bottom here? Grams of KOH. And what unit would need to go on the top?
Moles.
Moles of KOH. So what numbers go in there? What number goes with the mole? 1, because remember the 1 goes with the Mole, the one goes with the mole. Okay, that's our new song. And what number goes with the grams?
50.1.
56.1. Excellent. 203.082 divided by 56 equals 3.62 moles of KOH. And then the third thing we want to do is we want the concentration of KOH. I didn't leave myself room up there, so I'm going to rewrite the formula. I want the moles of KOH over the volume of solution. The reason I wrote it up there is so that, you know, we could just figure out that we needed moles of KOH. You don't have to write it till the end though, okay? Volume of solution, and we have 3.62 moles. And now we have to go back to our question and say, what is our volume?
2.00.
2.00 liters divided by 2.00 liters. Can I just leave it like that? Is that a complete answer?
Nope.
No, in chemistry, what do we have to do? We have to actually do the division. You can't just leave it as a fraction. Okay, you have to go 3.62 divided by 2 equals 1.81. And it's your choice whether you write, what are the 2 units?
Molar.
Molar, or you could write
Moles per liter.
moles per liter. Is good? Okay. So over the weekend, I would like you to do question number 1, 2, 3, 4, 5. Just numbers 1 through 5. Okay. On pages 57 to 58, because mostly what I want you doing, that should take you, like, you should be able to finish that before the end of class today. Mostly what I want you doing is I want you doing, do I even want you to do that today? Or do I just want you to do that other thing? Pages 47. This is a big chemistry weekend. Did you guys finish 45, 46? Excellent. So it's going to be 47 up to 53. Or no, sorry, 54. Pages 47 to 54. What I would advise is that you do like every second question. Do every second or third question. Yes? Because otherwise there's so many. Okay, so you're going to be like, I'm either going to do like this question, then skip one, and then this question and skip one, or I'll do this one and skip 2, and this one and skip 2. And you know what? I'm going to take this out. We will do that on Monday. Okay? Because you have a quiz on Tuesday, and this is going to be key for it. And you need to come on Monday with questions to ask about it if you have any. Okay? So it is vital. This unit, up until now, Chemistry 11 has been like skipping through the park, looking at the flowers, right? Oh, it's all just like grade 10. This stuff can mess you around, okay? If you get it, you get it. But if you don't get it, you need to know, and you need to come see me during flex, and you need to talk to me on Monday during class, and you don't want to get messed up, okay? This unit, some people can go from like a happy little B to like a C minus, right? Because all of a sudden it's like, I didn't have to practice up until now. Now I actually have to practice. So make sure you do that practice so you don't end up being that person who's like, I had a nice 77% and now I have 57. That would suck, okay? So this is where work ethic needs to come in. Yes.
Would the mega mole review help?
The visual review can help a little bit, yes. I would say in the next review, you would be looking at to number, yes, to pages 91 and 293. Okay, but it won't be sufficient because it doesn't kind of get into the more complicated ones here. And honestly, if you want to do every single question on pages 47 to 54, whatever, I'm not going to stop you for sure. But I realize that most of you have other things in your life besides chemistry and maybe don't have the time to do that. So we have almost 20 minutes right now, so you should get started on that now so you don't run out of time. I just enjoy that process so much. Oh, do you want to come up? It was better yesterday. It was prettier yesterday, but it's really cool. So,
Oh, the blue's gone.
the blue is gone now. Did you guys see the blue yesterday? Okay, so what's happened is that all of the complex plus ions, we've had single replacement reaction. You guys remember what those are from grade 10? So that's what gave us the next unit. And so the copper grabbed some electrons from the aluminum. The aluminum is now turned up into ions and it's dissolved in the solution. You can actually see this one. You're starting to get crusty salt on the top. That's aluminum sulfate. Okay. So if we let this dry out, we would have, instead of copper sulfate and aluminum, we would have aluminum sulfate and copper. Yeah. So this was
beautiful.
It's still like, oh, oops. Well, you know, good thing it's not toxic anymore. And it's pretty cool. Like, I don't know, how to say. The red is the copper. Yeah.
Maybe please go to the bathroom.
Oh, for sure. If you look on the top of this one here, you can see some really beautiful shiny copper floating on the top. Yeah. And if we were to wash it all off, it might look like that. But usually it looks kind of more reddish. I don't know why exactly. Yeah. It's kind of just fascinating. So that's how critical watching was just one. Yeah. Yeah, right? I think I'm actually gonna use it. We have an experiment next year where we take copper solid and we mix it with nitric acid to get some NO2 gas, which is a ground gas, and we do an equilibrium experiment with it. And we watch the gas turn colorless, not colorless. So like this is like so multi-purpose, right? Like you can go from this lab to this cool thing, that maybe thing here. Let me show you how to do that. Yeah, exactly. We don't have to climb on the ladder. Okay, very good. Anyone else want to see the copper that I recovered from the copper sulfate? So this is what I got. I put it into that blue stuff. I dissolved it. And so did copper plus copper sulfate. And then I added some aluminum. And then the aluminum did a single replacement reaction. So now instead of having copper sulfate, we have aluminum sulfate. And actually one of the mechanisms, the aluminum sulfate started to crystallize. And then left over. Oh, yeah.
It definitely is. Eventually, don't know the first second course. There's like, oh, my dad never lost it. So this is.
No, no.
Any questions? Oh, Scott, this is the copper we collected.
This is
Yeah, so we,
toxic or
no,
not
it's
anymore?
just, not anymore, now it's just copper metal. And, I need,
pure.
yeah, just pure copper metal. And I washed it a little bit, just so we got rid of some of the gunk that was on it. And now we're gonna dry it, and I'm collecting it in a little container so that next year, we can use it for something else. So if you're in my Chem 12 class, we will be using this
I'd
to
love to.
generate some, NO2 gas when we react it with nitric acid.
Such a beauty class.
I know. It'd be fun.
Oh, it's too long. You're so silly.
Ah, this is right, so together that's all.
Depending on who's
So one more. Or how many more? Would you say 18?
I know, that's why. I'm saying. I mean, they can't open doors over. They can't open. What's the massive one? It should be done. Yeah, they can't leave it on the, yeah, they can't.
Yes?